Greetings of the day. I am Dr. Unika Parmar and I welcome you all to today's lecture on Introduction to Field Effect Transistor and Junction Field Effect Transistor, that is JFET. Today we are exploring the exciting world of junction field effect transistors or field effect transistors. Field effect transistors are known as FETs and we will be covering two important topics today, that is JFETs and MOSFETs. JFETs stands for junction field effect transistors and MOSFETs stands for metal oxide semiconductor field effect transistors. So, these are the outlines for today's lecture. We will start with introduction of field effect transistors, features of field effect transistors, disadvantage of field effect transistors, classification of FETs, important terms in FETs, construction of junction field effect transistor, that is JFET, and construction of MOSFET, that is metal oxide semiconductor field effect transistor. The field effect transistor is a semiconductor device whose operation consists of controlling the flow of current through a semiconductor channel by applying an electric field, that is a electric potential which is calculated in voltage V. Usually, a field effect transistor is a three-terminal semiconductor device in which current conducts via one type of charge carrier, either holes or electrons. The current is conducted by only majority carriers. Unlike the usual BJT, bipolar junction transistor, the flow of current is controlled by means of an electric field, that is controlled by the effect of electric field developed between the gate electrode and the conducting channel of the device. The operation of a field effect transistor FET device is based on the electric field intensity produced in the channel. It is a voltage control device, means the current flowing through the channel is controlled by the voltage applied to the gate terminal. FETs have a high input impedance, typically greater than 1 mega ohm. The input impedance plays a very major role in electronic devices. So, the characteristics of the FETs, that they have high input impedance, make a very good choice in the semiconductor industry. In most measuring instruments, FETs are connected to the input side to offer large input impedance. As I told you, they have high input impedance. So, FETs are connected at the input side of the device, so they provide large input resistance. They have very small power dissipation, making them suitable for low power application. As the power draining capacity of the JFETs is very small, a very small amount of power is drained due to these FETs. So, they are very suitable in the condition where the battery life constraint is a big issue. So, they have very small power dissipation. So, this makes them suitable for low power applications. FETs are unipolar device, means they only have one type of carrier, that is electron or holes. Basically, these FETs work with majority carriers only. If the majority carriers are holes, so the flow of current is due to this hole current, or if the majority carriers are electron, then the flow of current will be due to the electrons only. So, this makes them a unipolar device. They are majority carrier devices, means the majority of the carrier in the channel are either electrons or holes. There are no minority carrier present in the field effect transistors. They are very less noisy device than bipolar junction transistor due to the absence of the minority carriers, as all the current flow is due to the presence of the majority carriers only. So, the chances of occurring noise in the device is reduced. Hence, the current flow is due to the majority carrier only and the device becomes less noisy. FETs have no leakage current, leading to less temperature effect on the device and excellent thermal stability which is higher than BJT's thermal stability. So, in the case of ICs where temperature plays a very important role, in the case of semiconductor temperature plays a very significant role, as we have seen in the earlier lecture. So, the temperature effect in the field effect transistor is quite less, hence it makes them thermally very stable and they are suitable for the condition where thermal fluctuation is larger. Hence, FETs are suitable for this thermal applications. FETs are typically fabricated on silicon. FETs have zero offset voltage. They are excellent in signal choppers. FET offers a large bandwidth, resulting in excellent reproduction of the input signal. The gain bandwidth product of FET is constant. The gain bandwidth product of BJT is greater than FET. Although FETs have large bandwidth, but the gain bandwidth product in case of BJT is higher than field effect transistors. So, they are used in the application which requires gain bandwidth product, but BJTs are more preferred where the gain of the circuit is an important factor. BJTs have higher gain than FETs. In comparison to BJTs, FETs are smaller in size and are easier to fabricate. The FETs are fabricated on silicon and the size of the FET is smaller than a BJT. So, where there is an area constraint, we use FETs rather than BJTs as they are easy to fabricate. One of the main disadvantage of a field effect transistor is that they have a smaller gain comparison to BJT. This is because the gain of the field effect transistor is determined by the ratio of drain current to gate source current, while the gain of BJT is determined by the ratio of collector current to the base current. Due to this, FET typically have low overall gain than bipolar junction transistor, which can limit their application in certain circuits. Additionally, the smaller signal gain of FETs also result in a smaller gain bandwidth product, which means that they may not be able to handle high frequency signal as well as BJTs. There are basically two types of field effect transistors, FETs. One of them is junction field effect transistor, it is referred as JFET, and the second one is MOSFET, it is referred as metal oxide semiconductor field effect transistor, MOSFET. Both the types of FETs are categorized to N channel or P channel depending upon their construction. Furthermore, the MOSFET type is further categorized into depletion type and enhancement type. So, this is the bifurcation of field effect transistor to various categories. So, the first category to that is a JFET, junction field effect transistor, and the second category is metal oxide semiconductor field effect transistors. All the changes here are due to the presence of the electric field. So, field effect transistor, the name itself specifies that we are working with the electric field and all the transistor action is due to the presence of this electric field. Hence, the name is given field effect transistor. Now, they are categorized in two sections, junction field effect transistor and metal oxide semiconductor field effect transistor. This category is due to the construction of these devices. Now, the junction field effect transistor only have depletion mode, while the metal oxide semiconductor field effect transistor, that is MOSFET, has depletion type and enhancement type. Now this bifurcation is again redivided into p channel and n channel. All the devices, the JFET and the MOSFET are again bifurcated into depletion type and enhancement type. All are again categorized to n channel and p channel type of devices. These are the symbol for a n channel JFET, then a p channel JFET. Then the next symbol is for depletion type n channel MOSFET and p channel MOSFET. The next is enhancement type n channel MOSFET and a p channel MOSFET. So there are few important terms which should be discussed before going in the operations of the field effect transistors. So the first one is source. It is the terminal that forms a connection with one end of the channel. Basically, the source terminal provides the majority charge carrier whose movement generates the current through the device. Drain terminal is again an important point in the case of a field effect transistor. Drain terminal is present at the opposite end of the source terminal. The majority carriers move from the one end to the another end, and they are all collected at the drain terminal of the transistor. So the electron starts to move from the source terminal and via the channel they come to the drain terminal. Hence the source end forms the one end of the channel and the drain forms the another end of the channel. Next term is gate. This terminal is formed by the combined connection of two heavily doped diffuse region over the substrate. The voltage that controls the level of current is provided at gate terminal. The next term is channel. The channel is the region present between the gate and the source terminal through which the movement of majority carriers take place. So let us discuss about the construction of a junction field effect transistor. The JFET is a 3-terminal device with one terminal capable of controlling the current between the other two as shown in figure 2. The JFET are of two types, including the N channel and the P channel junction field effect transistor. So the first diagram is for a P channel JFET and the second one is for an N channel JFET. Here we can see this, there are 3 terminals, gate, source and drain. So if we see from the integrated circuit, there are 3 terminals. The red one displays the source terminal, the blue one displays the gate terminal and the yellow one shows the drain terminal. The basic construction of N channel or a P channel JFET junction field effect transistor, their representation is shown in figure 3. So this is the structure for a junction field effect transistor with N channel and P channel. So in the symbol we can see that there is a arrow present at the gate terminal. If this arrow is inward, the device is a N channel JFET. If the arrow is outward, the device is a P channel JFET. Here we can see the flow of current. Flow of current is always from the source to the drain. So in the first figure and the second figure, we will observe in both the cases the flow of current is from source to drain and the gate terminal controls this flow of current. Generally, a N channel JFET is preferred. In an N channel JFET consisting of a N type silicon bar with 2 islands of P type semiconductor material diffused on the opposite sides of its middle part, thus forming 2 PN junction like as they are formed in the case of diode. Hence, there will be a N type of silicon bar with 2 two p-type semiconductors present there and it will form like an island. So, there will be two p-n junction formed there and this forms the construction of a JFET. The two p-type regions are connected with each other externally or internally and are named as gate. The ohmic contact are made at the two ends of a p-type semiconductor bar. One terminal is known as source, through which the majority carriers enter the bar, and the other terminal is known as drain, through which this majority carrier leaves the bar. So, source is the terminal where majority carrier enter in the bar and drain is the area where majority carrier leaves the bar, and this flow of electron or the flow of majority carriers is from source to drain via a channel, and this channel is controlled by the gate terminal. In essence, therefore, the drain and the source are connected to the two ends of n-type channel and the gate of two layers of p-type material. Thus, a junction field effect transistor has essentially three terminals called the gate, source and drain. The silicon bar works like a resistor between the two drain and source terminal. The gate terminal is similar to the base of an ordinary transistor. It is used to control the flow of current from the source to the drain terminal. Thus, source and drain terminals are similar to the emitter and collector terminals of a bipolar junction transistor. So, this is the construction for a n-channel JFET as shown in figure 4. Here we can see that there is a silicon bar which is of n-type. See, it is a n-channel JFET, so the silicon bar will be of n-type and there are two islands of p-type. So, these p-types are because of the diffusion of the holes, making it a p-type material. So, there are two p-type materials and a one n-type material, and the connection D represents the drain terminal and the connection S represents the source terminal, and the p-type connections are provided with the gate. They are connected to each other forming the gate terminal. The flow of the majority carriers. Here, as it is a n-channel JFET, the flow is due to the electrons. So, the electron on applying the appropriate potential at the gate terminal will start to move from the source terminal and they will move towards the drain terminal, and here the flow is of electrons, that is the majority carrier. Always remember, in case of a field effect transistors, the current flow is due to the majority carriers only, and these carriers are unipolar. These devices are unipolar devices. Because of these devices are unipolar devices, they have very less noise in the circuit. So, here we can see that there are three terminals, source, gate and drain, and the current flows from source to drain, and this flow of current is controlled by the gate terminal. As mentioned, the MOSFET is basically classified into two forms. They are depletion type and enhancement type. The MOSFET is also available in both type, N channel and P channel. N channel are generally referred as NMOS and P channel are generally referred as PMOS. Their symbol is shown in figure 5. So, this is the symbol for a metal oxide semiconductor field effect transistor. The first one is for N-type MOSFET, that is N-channel MOSFET, and it is also referred as NMOS. In general terms, we call it as NMOS. And the second one is for a PMOS. PMOS refers to a P channel is known as metal oxide semiconductor field effect transistor. So here we can see there is a classification between the enhancement type and depletion type. So here we can see that the figure for the enhancement type MOSFET and the second one is for a depletion type MOSFET. So the difference between the enhancement and depletion type is that the channel already is being fabricated in case of a depletion type MOSFET, while in the case of an enhancement type MOSFET, the channel is not present, the channel is not fabricated. So when the channel is fabricated, it is a depletion type MOSFET, and when the channel is not fabricated, it is a enhancement type MOSFET. So as I told you, the channel is already fabricated in case of a depletion type MOSFET. So while the MOSFET is being made, we already fabricate the channel, that is we already provide a doping for the channel region, hence it forms a depletion type MOSFET. While in the case of enhancement type, no extra doping is provided for the formation of channel, hence there is no channel which is already existing in the device. The channel is formed because of the electric field due to the gate terminal and the source and drain terminal, the overall electric field because of the presence of the gate voltage and the source drain voltage. So a channel is formed due to this overall electric field, hence no additional channel is fabricated in case of an enhancement type MOSFET. Hence in an enhancement type MOSFET, we does not have a channel, while in case of a depletion type MOSFET, we have a channel existing in the device. Again we can see there are various arrows which signifies whether the device is a P channel MOSFET or a N channel MOSFET. So in the case of a P channel MOSFET, the arrow is outward. The arrow is present at the gate terminal and it is outward, while in case of a N channel MOSFET, the arrow will again be present at the gate terminal, but in this case there is a difference. The arrow will be present at the inward end, that is the arrow will be inward to the transistor. In the case of a N channel MOSFET, the arrow is inside, while in the case of a P channel MOSFET, arrow faces outward. So these are the symbols for the enhancement type NMOS and enhancement type PMOS, and then is depletion type NMOS and depletion type PMOS. The construction of MOSFET is very different as compared to the construction of a junction field effect transistor. In both enhancement and depletion mode of a MOSFET, an electric field is produced by the gate voltage, which changes the flow charge carrier, such as electron for N channel and holes for P channel. The simple side view of a N channel MOSFET is shown in figure 6. The left figure shows its construction detail. The source and the drain terminal are connected through a metallic contact on a N doped region linked to a N channel. The gate is also connected to a metal contact surface, but remains isolated from the N channel by a very thin layer, usually of silicon dioxide. the fact that the deposited SiO2 layer, silicon dioxide layer, is an isolated layer reveals that there is no direct electrical connection between the gate terminal and the channel of the metal oxide semiconductor field effect transistor, that is a MOSFET. The input impedance is very high in the case of MOSFET. There is no connection between the gate and the channel as it is separated by a silicon dioxide layer. Hence, it has very high input impedance, that is, it is in the range of 10 to the power of 10 to 10 to the power of 15 ohms. So, here in the figure we can see there is a source terminal, and a drain terminal, and there is a layer of the body. The S represents the source terminal and D represents the drain terminal and G represents the gate terminal. Metal oxide semiconductor. In the gate region, there is the layer of metal and then oxide, and below to it is the semiconductor. There is no connection of the metal with this semiconductor as a oxide layer is present between them, and as there is no connection from this input terminal to the semiconductor, the input impedance turns out to be very high. So, there will be a large rectification of noise due to the presence of this input impedance in the device. Hence, the device has high input impedance. So, this was about the construction of a metal oxide field effect transistor. Now, all the FETs, field effect transistor, whether it be MOSFET or JFET, they have first of all high input impedance, and second, they are excellent for switching ability. Why is they are excellent in the case of switching ability? Because they are unipolar devices. There is no role of generation and recombination present here. Current flow is only because of the majority carriers. There is no role of minority carriers present in such devices. Hence, the device have excellent switching capacity because of only of the majority carrier in the device. So, because of the presence of these majority carriers, there is no role of minority carriers, hence there is no process of generation and recombination. Hence, the devices has high switching speed. Let us discuss about the difference between BJT and FET. BJT stands for a bipolar junction transistor, while FET stands for field effect transistor. The operation depends on the majority carriers and minority carriers in case of BJT, while in the field effect transistor the operation depends upon the majority carriers only. So, either with the holes or with the electrons. In the case of the input impedance, BJT has very less input impedance and it ranges from 1 kilo ohm to 3 kilo ohm, while in the case of FET, it has very high input impedance. A BJT is a current control device, while a FET is a voltage control device. It is controlled by the electric field. As the input impedance is less, so BJT is more noisier and the FET is less noisy. The frequency variation in the case of a BJT affects the device performance, while in the case of a FET, it has high frequency response. BJT is temperature dependent and FET has high thermal stability. BJT is cheaper and FET is costlier than BJT. The size of a BJT is comparatively larger than FET, while FET is smaller than a BJT. BJT has an offset voltage while FET has no offset voltage. The gain of the BJT is much high in comparison to the FET. FET has lower gain. BJT has high output impedance because of its higher gain, while FET has low output impedance because of less gain. Its collector and base are more positive than the emitter, while in the case of a FET, drain is positive and the gate is negative with respect to source. In the case of BJT, the base is negative with respect to emitter, while the gate is more negative with respect to source. BJT has three parts: base, emitter and collector. FET has drain, source and gate. The gain is very high in case of a BJT. It is high voltage gain and low current gain, while FET has low voltage gain but high current gain. The switching time is medium in case of BJT, while FET the switching time is fast. The BJT is easily biased while FET the biasing is difficult. The BJTs are preferred for low current application while FETs are preferred for low voltage application. BJT requires small amount of current to keep on. The FETs requires small amount of voltage to keep them on. The BJT consumes more power and has negative temperature coefficient, while FET consumes less power and have positive temperature coefficient. So, this was the difference between the BJT and FET. So, thus today we have discussed about the field effect transistors. Field effect transistors are generally known as FETs also. We have discussed about the features of the field effect transistors. We have discussed about the classification and their advantages and disadvantages. We have also discussed about the important term or the major terminologies in this field effect transistors, as well as we have seen the construction and working of the JFET, and we have discussed about the construction of a MOSFET. MOSFET is metal oxide semiconductor field effect transistor and JFET is junction field effect transistor. Hoping to see you in the next class. Thank you for your patience listening.